Hello and welcome to this presentation. My name is Eddie Hill. I am an applications development engineer within the mining sector of the Natural Resources Group in ZEISS. Today I would like to speak to you about gold recoverability, how the morphology of the gold grain and its hosting characteristics are determining factors in the recoverability of gold when the grain size is in the micron range or sub-micron. We use gold and gold ore as examples throughout this presentation, but in reality, this will be applied to many precious metal ores. I will introduce the challenges that we're presented with analytically, and I will also introduce some of the developments we have executed within ZEISS to aid in these analysis and in understanding the challenges. But rather than talk just about the solutions, I want to put you through a couple of test cases. In the first test case, we would talk about the application of automated quantitative mineralogy to sub-micron gold samples. In the second test case, we will be looking at gold as a trace mineral in an ore and accounting for losses of this phase into the tailings. I will then summarize our conclusions. The processing of gold ores presents several challenges. The gold deposit itself can display mineralogical and textural variability. The intricate nature of the ore can then be described in terms of the variability of the gold-bearing phases, whether this is native gold, electrum, telluride, some form of arsenide, or a combination of all of these. The granulometry, or how the grain size of the phases of interest changes, and the ore's mode of mineralogy. In effect, what other elements exist in the gangue that are going to affect our recovery of the gold. All of these characteristics, individually or as a group, may interact to cause refractoriness by a variety of mechanisms. Causes for refractoriness, or the affinity of the gold to remain in the ore material rather than be recovered, are multiple. And it may be that any one of these causes is impeding the recovery, but likelihood is that many of them interact to cause refractoriness. Changes in mineralogy of the gold phase composition may be a cause of refractoriness. Changes in grain size may require grinding adjustments in order to maintain the liberation indices. Changes in the gangue composition may affect the gold's textural setting or the gold-bearing phase's textural setting. It may be that its mineral association changes, it's no longer associated with silicates, and now we suddenly find it encompassed within sulfides. We may experience passivation when soluble coatings on the gold-bearing phase inhibit the leaching reagent. Decomposition, where other phases are present, particularly those that contain copper, zinc, lead, arsenic, and antimony, are consuming the reagent and so making it less effective at leaching out the gold. Or preg robbing, where gold absorption by naturally occurring carbonate rob the gold from the pregnant alkaline cyanide solution. Routinely, microscopy is used to study these challenges and to assess how good our recovery process is. But there are challenges presented to any current microscopy technique. There's challenges when using the light microscope in its ability to study the smaller grain sizes. And because it's a manual process, there may be a bias induced by the operator, even unknowing bias. With the scanning electron microscope and automated mineralogy, the challenges have changed. We no longer expect a bias from the operator, but analyzing a single 30mm metallurgically prepared sample may not be sufficient to be to provide statistically viable data. It may be that sufficient gold grains are not studied. Also, there's the serological correction required, which may induce its own slant on the data. And traditionally or historically, there has been an inability to account for submicron grains consistently and reliably. Over the next two work cases, we're going to present how advances in automated quantitative mineralogy and the X-ray microscope have overcome the issues presented by submicron granulometry and the statistical representativity of the samples. Now I would like to talk through test case one, which will apply automated quantitative mineralogy to the study of submicron gold samples. But first, I would like to explain what ZEISS means by automated quantitative mineralogy. How does it differ from automated mineralogy? So it still automates the scanning electron microscope, the SEM, to perform an automated analysis of a geological sample, a mining sample. But rather than using peaks on a spectra or impulses through an amplifier to determine our phase classifications, we use a precise chemical analysis and the morphology of the sample to provide automated petrological analysis. Our classification is mainly based on quantitative use of DDS detectors. And this will mean that what we obtain is a full spectrum that we then deconvolve and obtain a chemical analysis of any one point analyzed. And it is that chemical composition that in principle determines the mineralogy. This means that our classifications are independent of the system being used and can be shared freely between any mineralogic system around the world, as they are solely based on chemistry. Since we have a chemical composition, we can then assign elemental ratios to that classification to further tighten the discrimination of the phases being analyzed. We can also make maximum use of all of the detectors on the SEM. And in the case of the grayscale produced by the backscatter detector, we can add this to the classification library. And so we can discern between phases that may have a similar chemistry, but may be a hydrous phase. We can't, with EDS, obviously analyze for hydrogen, or maybe a carbonate. And since we carbon coat, we're not analyzing for the carbon itself. And so perhaps something like a goethite and a siderite may seem similar in composition, since we're ignoring the chemistry and the water in one of them, and the other. But the gray level will then also help us discriminate between them. And so we can precisely classify them both. And finally, we can add morphological parameters to this classification. This is what we call morphochemistry, where we can differentiate between two habits of the same phase. So we have an acicular habit and a tabular habit. We would be able to discriminate and classify between these. And this is some of the ability that we have used in order to be able to perform these analyses. Over to the test case itself. Case one presents a classic example of the application of AQM, automated quantitative mineralogy, in the analysis of ores. The mine has seen a drop in the recovery and has realized that the mineralization is not fully understood. The lack of knowledge of the mineralogy, grain size, and the mineral associations at play. And questions are being asked regarding the composition of the tellurides that have suddenly appeared. They don't know what tellurides they have, but they have detected tellurium on a fluorescence analysis. And they don't really understand the hosting characteristics of this tellurium, or the gold telluride they believe exists in their sample. We're provided with 3 samples from different sections of the mine to be analyzed. The AQM analysis was performed by ZEISS mineralogic mining, and mineralogic mining measures, as we've described, the morphological parameters, chemical and physical features of the sample during the analysis to provide a precise classification and quantification. Here on the right-hand side, as you can see, we have the bulk mineralogy output, or part of it anyway, for the samples analyzed. This stubs 1 through to 3. We can see the phases encountered at each case, the number of instances of that phase in the sample, the area percentage they provide, or the weight percent. We know what the chemical composition of the sample is, we know what the specific gravities are, so we can easily calculate what the weight percent distribution of the different phases present is. We provide an average of the grain size for each phase and the standard deviation on that average. Of course, in the database, the grain size of each individual of the 14,439 grains of quartz exists and can be studied at the operator's leisure. We also immediately provide an average weight percent composition for each phase. And this table is presented immediately at the end of the analysis. There's no post-processing required. As a quick guide through, the gangue is dominated by quartz, pyrite, and mica. And the gold-bearing phases are native gold, electrum. There's some silver. There's a petzite, that's a silver gold telluride, hessite, that's a silver telluride, some empressite, again, silver telluride. And then we have calaverite and sylvanite as gold tellurides. On the right-hand side, we have charts for the distribution of gold between the three samples. And it's obvious that in stub 1 and stub 3, very dominant is native gold. In stub 2, we have some petzite and a contribution from calaverite in this sample too. Immediately underneath, we have a grain size distribution, and this ranges from 200 nanometer grains up to larger than 10 microns. Obviously, gold is the more present phase, and the majority of the gold appears to be present in the 1 to 2 micron grain size. And this is similar for the calaverite and the petzite. However, there are significant contributions at sub-micron size also. Another one of the immediate outputs at the end of the analysis is the liberation table. And here we can see that calaverite is majorly locked, as is native gold. And the petzite seems to be the only phase that is fully liberated, or the key phase that is fully liberated in these samples. Now, with this information, we can consider the parameters causing refractoriness. We can evaluate them. And we find that decomposition is unlikely, as the sum of phases that may induce it contribute less than 1% of the composition of any one sample. There are hardly any copper sulfides, for example, in these stubs. The same can be said for preg-robbing. The level of carbonates present is below 1% in either sample. The gold mineralogy is reasonably constant across the samples, as is its grain size. But however, liberation is an issue, with 66.9% of native gold being locked. So if we look at the associations of the gold-bearing phases and native gold itself to within themselves, but also to other significant gangue phases, what we find is to resolve the lack of liberation, it shouldn't be too difficult in this instance. Native gold has an important association with quartz. Here we are. And a lesser one with pyrite. Therefore, it's likely that in order to liberate the gold, all we need to do is grind further. There's an issue of granulometry. The tellurides have no or minor association with quartz, as we can see for the rest of the samples along this row. However, they have major associations with pyrite. And in this instance, if we do want to recover the tellurides, we would recommend baking. And so we see how some analysis using automated quantitative mineralogy, even of sub-micron gold, help us discern what the best way to proceed is with an informed way rather than guessing what the best or next test to try would be. Test case 2 is slightly different. In this case, we compare the automated mineralogy analysis performed in the past for the mine to an XRM of 3D analysis of the gold tailings. Sample A was analyzed by mainstream automated mineralogy techniques, but sample B was analyzed by ZEISS X-ray Versa XRM. Both samples are of the smaller than 20 micron size fraction, and processing of the ore involves flotation concentration step. The ore itself reports for sample A at 18 grams per ton gold. The sample was prepared as a 30 millimeter stub and mechanically ground and polished, and this proved significant. 10 gold particles were found, by which we assume that the analysis is statistically viable. These were smaller than 5 microns in cross-section. They were liberated. We encountered low association to charcoal pyrite. And the assessment is that these particles should have been recovered by flotation. However, many of these particles reported to the tailings. So the results indicate an unrecognized influence. Look at sample B. Here we're looking at 0.13 grams per ton gold. The sample preparation for XRM is a non-mechanical preparation. We simply pour the sample, the ground sample, into a tube to contain it during the analysis. The scan took 90 minutes and measured over 90,000 particles in 3 dimensions. We have entire volume and phase recognition. Over 26,000 particles of pyrite and 3 gold particles in the tailings. What we found is that the gold grains that reported to the tailings are roughly 20 microns in size. They're elongate and associated with clays. Now, these clays were likely removed during the mechanical sample preparation for the 2D analysis when we prepared the metallographic plugs. Now, the morphology and particles here are consistent with particles that would be slow to float, and therefore it is believed that due to the kinetics of the process, they were missed, and this is why they report to the tailings. And we see here a scan through the 3-dimensional volume of the sample, and the red particles are pyrite, and when we remove them, we're left with the 3 gold grains that we found. There we see the cigar shape of these particles. And so I have presented 2 test cases, one in which using automated quantitative mineralogy provides all the answers that we need in order to discern the challenges presented to the mine. However, this is not always going to be the case. Using a 2-dimensional analysis system where the storological influences are not always recognized isn't always going to provide us with the answer that we need. And therefore, a combination of AQM and XRM is probably the best means by which to proceed. However, automated quantitative mineralogy techniques such as mineralogy mining do provide a precise and detailed analysis of the chemical composition, the mineralogy, text and morphology of the ores, which cannot be obtained simply through XRM. Now, this flexibility and the processing power allows us to deal with sub-micron particles and grain boundary issues. And thus, we make it available crucial information about the ore body and its processing characteristics. In contrast to the main mineralogical characterization of ores, which can be easily done by the AQM, accounting for trace mineralogy in low-grade gold deposits or determining the reasons for gold losses to tailings, analysis is best performed by XRM. Here, we get to understand the gold grains completely because we study them in 3 dimensions. We study the whole volume. We can see the associations. We're not deforming them mechanically during sample preparation. And so we obtain a different level of information that is complementary to that provided by AQ. And with this, I conclude my presentation. I hope you enjoyed it. And please contact us with any questions you may have.